You know, if you grew up watching movies like The Terminator or Iron Man, you probably have this very specific image burned into your brain of how machines see the world.
Oh, absolutely. It's always that incredibly crisp, dynamic heads-up display.
Right, exactly. You've got this perfect 3D geometry, just like mapping the environment in real time, little boxes locking onto moving
So it's
targets.
calculating distance and speed instantly.
Yeah.
Yeah.
Hollywood makes it look so effortless, you know? Like machines just naturally perceive the physical world with absolute flawless precision.
It's a great visual trope, but let's be real. The reality of engineering that kind of vision has been anything but effortless.
Definitely.
Giving a machine true spatial awareness is actually one of the most stubborn, computationally expensive, and just physically clunky challenges in modern robotics.
Which brings us to today. Welcome to the Deep Dive Lab, where we're taking a deep dive into the underlying mechanics of machine vision.
Glad to be here for this one.
We're looking at a stack of freshly published research today that essentially solves a problem scientists have been, well, basically banging their heads against for years.
Yeah, it's a massive breakthrough.
Because here's a strange question for you, the listener. You have an incredibly powerful, cheap, high-definition 2D camera sitting in your pocket right now on your smartphone, right?
Which we can manufacture by the billions, easily.
Exactly. So why don't we have the equivalent of a cheap, tiny, solid-state 3D camera for machines yet? Like, why is the 3D part so absurdly difficult?
Well, to really understand the difficulty, we have to look at what the industry originally adopted as the ultimate solution, which was time-of-flight LiDAR.
Okay, time of flight.
Right. And if you've ever seen those early prototypes of self-driving cars, you definitely know what this looks like. They have those giant spinning buckets mounted right on the roof.
Oh, yeah, they look like oversized police sirens just spinning around at 100 miles an hour.
Exactly.
But wait, if moving parts are the main issue, why not just build a stationary flash LiDAR? Like a giant camera flash that illuminates the whole street at once. No spinning required.
I mean, that seems like the logical fix, right? But the problem is the physics of light scattering.
Okay.
Flooding an entire environment with enough light to bounce back from, say, hundreds of meters away requires massive battery-draining amounts of power.
Ah, I see.
Plus, when you illuminate everything all at once, the returning photons just scatter into the wrong sensors on your chip. You get unbearable crosstalk.
Like trying to listen to one specific whisper in a crowded stadium where everyone is shouting at the same time.
There's a perfect way to put it. So to avoid that crosstalk and save power, engineers realized they had to use a single, highly focused laser beam and actually move it.
Okay, let's unpack this for a second, because on the surface, spinning a highly focused laser around works, but the energy required to do that physically is just intense.
It's huge.
It's like trying to map out a giant pitch black baseball stadium by running around in circles carrying a single massive spotlight.
Right.
I mean, you will eventually map the stadium, but it's exhausting, it's inefficient, and if you trip and drop the spotlight, the whole system goes blind.
Exactly. Those mechanical spinning systems require microjoules of energy per single point of light.
Wow.
And that adds up incredibly fast when you're shooting millions of points a second.
Yeah.
Furthermore, they rely on highly calibrated, rapidly spinning mechanical components.
What you're putting on a car.
Right. When you mount that on top of a car bouncing through potholes at 60 miles an hour, things break. They vibrate, they're bulky, and they cost thousands of dollars to manufacture.
I imagine scientists realized pretty quickly that strapping fragile, rotating buckets to consumer vehicles wasn't the end game.
Oh, definitely.
They must have tried to build solid-state versions, right? Like just shrinking the whole thing down to a chip where nothing has to physically move.
They did try that,
Mhm.
predominantly using something called optical phased arrays, or OPAs.
Mm.
The concept was to use hundreds of microscopic emitters on a chip and steer the laser beam electronically.
Electronically, so no moving parts.
Right. They did this by tweaking the phase of the light waves so they would interfere with each other and angle off in a specific direction.
That sounds incredibly complex.
It was. Scaling that technology up turned into a total engineering nightmare.
Really? Why?
Steering a beam across a wide field of view using OPAs required huge amounts of power. But worse, keeping hundreds of microscopic lasers perfectly calibrated while the chip naturally heated up and cooled down, that proved nearly impossible.
Because heat changes the materials.
Exactly. The thermal drift would misalign the microscopic phases. So the scientific mystery became, how do you shrink a massive spinning bucket of lasers onto a tiny motionless piece of silicon without it melting, blinding itself with scattered light, or draining your battery.
And for a long time, that felt like an impossible wall to climb.
Completely impossible.
But that is exactly where the story takes a massive turn.
Yes, it does.
According to a study published in the journal Nature in March 2026, a team of scientists finally cracked the code.
And it's a brilliant piece of engineering.
Yeah, Dr. Francesca Fabiana Settembrini, Dr. Arif Khan Gungor, Dr. Remus Nicolescu, and their colleagues from Point Cloud GmbH in Switzerland, they managed to build something that honestly sounds like science fiction.
It really does.
They built a large-scale, coherent 4D imaging sensor.
And the scale of what they achieved here is really the breakthrough. They didn't just make a small proof-of-concept prototype.
Right.
They integrated an astonishing 352 by 176 pixels onto a single chip.
That's massive for this tech.
Yeah, to pull that off, they had to pack over 0.6 million microscopic photonic components, along with all the necessary electronic wiring, onto one small piece of silicon.
Wow.
It represents a 5-time increase in pixel count over any previous demonstration of this technology.
Okay, I have to grapple with the physics of this for a second. Over 500,000 components on one tiny chip.
Yeah, 0.6 million.
If you pack hundreds of thousands of microscopic lasers and sensors that tightly together, the thermal management alone seems impossible.
It's a huge hurdle.
How do you cram all of them in without the light bleeding over and blinding the adjacent pixels?
Well, they solved that by completely re-engineering the architecture of the pixel itself.
Okay, how so?
In older, bulkier systems, engineers typically used a bistatic setup. That means you had one lens or grating that transmitted the light out, and a separate one situated right next to it that received the bouncing light back.
Two separate eyes, basically.
Exactly. But when you try to shrink a bistatic setup down to the microscopic level, the light bleeding from the transmitter completely overwhelms the receiver.
Oh, I see.
It's like trying to stare at a filled star while someone shines a flashlight directly into your eyes.
Yeah, the crosstalk would render the chip useless.
Exactly. To fix it, the Point Cloud team used what is called a monostatic configuration.
Monostatic, meaning one.
Right. Using deeply integrated silicon photonics, they designed tiny structures called grating couplers to do double duty.
Oh, wait.
Yeah, the exact same microscopic structure that fires the laser beam out into the world is the exact same structure that catches the light bouncing back.
That is wild.
They used, the heat actively shunts the laser down specific pathways, sequentially directing the light to different specific groups of pixels on the board.
And it does this quickly.
It executes this routing so incredibly fast that the sensor can capture up to 15 frames per second.
That's incredible.
No moving parts, just heat and light dancing across 500,000 components. But the steering mechanism is really only half the genius here.
What's the other half?
The real paradigm shift is what the light is actually doing when it leaves the chip. Because this isn't just a 3D camera, it's a 4D camera.
Wait, okay, earlier you called this a 4D camera, but we've only been talking about mapping 3D space height, width, and depth.
Right.
Where does the fourth dimension come in? Are we, like, tracking time?
We are tracking velocity.
Oh.
When we say this chip sees in 4D, we mean it inherently knows exactly how fast an object is moving toward or away from it at the exact same moment it measures the distance.
But if it's just a tiny motionless chip, how does it simultaneously map the world and calculate speed better than the old spinning buckets?
This comes down to the core technology powering the chip, FMCW.
Which stands for?
Frequency Modulated Continuous Wave Detection. The old mechanical spinning buckets used time of flight. They fired a dumb pulse of light, started a stopwatch, and waited for it to bounce back.
Right. Pretty straightforward.
FMCW is vastly more sophisticated. Instead of a pulse, the chip fires a continuous beam of laser light, but it modulates the frequency.
Modulates it how?
It chirps the frequency up, and then it chirps it down. If you could hear it, it would sound exactly like a passing ambulance siren whose pitch is constantly rising and falling.
So it's essentially singing a very specific shifting note to the environment.
Exactly. And when that chirps light bounces off a car or a person and returns to the chip, it undergoes a process called heterodyne detection.
Hold on, heterodyne detection sounds like a spell from Harry Potter.
I know, it's very technical sounding.
What does it actually mean to physically mix returning light with original light? Are the light waves actually colliding on the chip?
They are literally colliding, yes.
Yeah.
When the chip fires the original laser beam, it splits off a tiny fraction of that light and keeps it internally on the chip.
Like a backup.
We call that the local oscillator. Think of it as a reference node, because the frequency of the outgoing light is constantly changing that ambulance siren we talked about. By the time the bounce light gets back from hitting an object, The outgoing laser has already moved on to a slightly different pitch.
Oh, I see where this is going.
Yeah. When you physically mix those two slightly different light frequencies together on the chip, they interfere with each other and create a beat frequency.
A beat frequency.
Right. By measuring the frequency of that interference pattern, the chip knows the exact distance to the target down to the millimeter.
Wow. And here's where it gets really interesting, the velocity part. The fourth dimension.
Yes.
How does the Doppler effect play into the up chirp and down chirp?
Okay, so if the object you're looking at is moving towards you, the Doppler effect compresses the returning light waves, shifting their frequency.
Like the siren getting higher pitched as it approaches.
Exactly. If the object is moving away, the waves stretch out. By comparing the beat frequency created during the up chirp with the beat frequency created during the down chirp, the mathematical difference between the two instantly reveals the target's exact radial velocity.
That is wild. It's not just taking a static 3D photo of a baseball being thrown at your head.
Yeah.
It's literally painting a speed limit sign on the baseball in real time as it travels through the air.
Yes, exactly.
It's a high-precision radar gun and a 3D camera rolled into one single pulse of light.
It really is.
But, a lot of these exotic optical physics experiments look great on a whiteboard and then completely fail outside of a pristine laboratory.
Oh, sure.
Did they actually test this in the real world?
They did. And the real-world performance metrics are what make this Nature paper so significant.
What did they do?
The team aimed this tiny chip out a window at an outdoor office scene. They successfully mapped the architectural details, the windows, and the facades of buildings located 65 meters away.
That's pretty far.
And they achieved a stunning 0.06-degree angular resolution.
Wow.
They also tested the velocity tracking on a rapidly spinning disk. The resulting point cloud accurately color-coded the speed of the different parts of the disk as it spun, proving the 4D capability works flawlessly.
And they did all this using extremely low power, right?
Very low.
The paper notes they used just 46 nanojoules of energy per point. To put 46 nanojoules into perspective, it's roughly the amount of energy required to power a single tiny LED light bulb for a billionth of a second.
It's practically nothing.
Yeah, nothing compared to the massive battery drain of spinning a physical motor on a car roof.
Exactly.
But I want to pivot here. If you're listening to this on your commute, having a tiny chip that can see 4D is undeniably cool science.
For sure.
But the history technology is a graveyard of brilliant inventions that failed simply because they couldn't be manufactured cheaply.
That is the harsh reality of hardware.
Right. So why is this chip any different?
Well, if we connect this to the bigger picture, the most disruptive aspect of this entire breakthrough isn't the physics itself, it's the manufacturing process.
Nelly. The manufacturing.
Yeah. The point cloud team fabricated this 4D sensor using standard silicon photonics infrastructure.
Meaning what exactly?
It means it is entirely compatible with CMOS manufacturing.
Oh.
CMOS is the exact same highly matured manufacturing process that already churns out the processors for your laptop and the 2D cameras in your smartphone.
That's huge.
There are already billion-dollar foundries around the world set up for this.
So they didn't just invent a new technology, they invented a new technology that can be built using the mass manufacturing factories we already have.
Exactly.
That is the holy grail of hardware engineering.
They successfully bridged the gap between exotic optical physics and mass consumer manufacturing. Furthermore, because this specific laser operates at a wavelength of 310 nanometers, it is completely eye-safe.
Oh, that's critical.
Right. You could have thousands of these sensors firing in a crowded room, and human eyes wouldn't perceive a thing, nor would they be harmed.
Good to know.
And because it uses that coherent FMCW detection we explored, where it only measures the interference pattern of its own internal reference laser, it completely ignores outside interference.
Oh, so like blinding sunlight won't affect it?
Blinding sunlight won't affect it. Other LiDAR systems on other cars won't confuse it. It only hears the exact specific chirp it sent out.
Man, the infrastructure of our world is about to get a massive upgrade in perception.
It really is.
Think about autonomous cars. Right now, they need those bulky, expensive roof racks to navigate.
Yeah, the spinning buckets.
With a CMOS-compatible chip, you could integrate flawless, invisible 4D sensors directly into the car's headlights or behind the rearview mirror.
Easily.
Or think about augmented reality. Current AR glasses struggle to map your living room without draining their battery in 20 minutes because they're relying heavily on computationally expensive 2D camera algorithms. A chip like this could instantly map your environment in true 3D with almost zero power draw.
And the security applications will fundamentally shift as well.
Oh, how so?
Well, current facial recognition can sometimes be fooled by high-resolution images, or it struggles in poor lighting conditions. But a coherent 4D sensor doesn't look at a flat image.
Because it's measuring physical depth.
Right. It maps the exact microscopic 3D contours of your face while simultaneously measuring the subtle velocities of your pulse beneath your skin or the micro-expressions in your muscles.
Wait, it can see your pulse?
The velocity tracking is that precise. You cannot fool it with a photograph or a highly detailed silicone mask.
It's the difference between looking at a painting of a face and physically tracing your hands over a sculpture.
Uh,
It fundamentally changes how machines verify reality.
it really does. So if we summarize the core breakthroughs we've explored today, there are two massive takeaways.
Let's hear them.
First, scientists have finally succeeded in miniaturizing 4D vision simultaneous distance and velocity measurement onto a completely solid-state, motionless chip using over 500,000 integrated photonic components.
Incredible.
Second, and most importantly for the consumer market, by designing this complex architecture to be compatible with existing CMOS chip manufacturing, they've paved the way for ubiquitous, cheap, large-scale 3D cameras.
The barrier to entry for machine vision just plummeted.
Exactly.
I think that highlights something really beautiful about the progression of science. It's not always about discovering a brand new, previously unknown law of physics.
No, not at all.
Sometimes the real revolution is about the magic of integration.
That's a great word for it.
It's taking massive, unwieldy, complex physics concepts like heterodyne laser mixing and Doppler velocity tracking and relentlessly engineering them until they shrink down so small that they can fit on a sliver of silicon in your pocket.
Right.
It's turning a room-sized experiment into a single, elegant chip that can be printed by the millions.
This raises an important question, though.
Oh, what's that?
A question of how we adapt to this new baseline capability.
Okay.
If this discovery is truly just the beginning of the CMOS 3D revolution, and soon every machine, every car, and every smart device around us has perfect, continuous 4D awareness of our exact distance and speed.
Which it sounds like they will.
Right. How will our physical environments and cities evolve to interact with machines that can suddenly see us with infinitely more precision than we see them?
Wow. That is a thought that definitely rewires how you look at the Terminator heads-up display.
Doesn't it?
We are building it, and it's going to be invisible, cheap, and everywhere. Thank you so much for joining us here in the Deep Dive Lab today as we explored the incredible shrinking of machine vision.
It was a pleasure.
If you enjoyed uncovering the mysteries of our world with us, be sure to follow and subscribe for more fascinating science stories. We will see you next time.